All right, 2005 E&M number 2. We have a circuit with an ideal battery, 2 resistors, an inductor, and a switch. And R2 and the inductor are in parallel. There are unfortunately also no numbers. So this will be a symbolic problem. All right. Determine the current through resistor 1 immediately after the switch is closed. Okay, the way inductors work is they don't like change. So right after the switch is closed, whatever the current in the inductor was before we close the switch, that's the current now. So if the current is 0 before, the current is still 0, and that means all of the current goes through R2. So for part A, R total is going to be R1 plus R2 at the instant that the switch is closed at t equal to 0. So resistor 1, the current through resistor 1 is going to get the total current. So we can say I total equals I1 equals the battery over the total resistance, which is R1 plus R2, and that's all we need, and we're done. Part B, the magnitude of the initial rate of change of the current in the inductor. Okay, now the inductor is in parallel with R2. So that means it has the same voltage across it that R2 has. So V2 is going to be I total, but only R2. So we're going to have, for V2, this will be battery over R1 plus R2 times R2. That's the voltage drop across R2. That's also going to be the voltage drop across the inductor. So for the inductor, VL, remember, is minus L di dt. And they have a very nice word here called magnitude, which means we can ignore the minus sign for right now. So L di dt is going to be equal to, remember V2 and VL are the same because they are in parallel, the voltage drop here, which is battery over total resistance times R2. And if we want just di dt, we can divide both sides by L, 1 over L, and there we go. We get the rate of change of current in the inductor at time t equal to 0. C, a long time after the switch has been closed. Now, a long time after the switch has been closed, the current through the inductor has reached its maximum, and it now acts just like a wire. So all of the current is going to be going through this branch on the right, and there's going to be no current through R2. So that reduces our current. If you take a look back up at part A, we have I total is the battery over the total resistance. Our total resistance is now just R1. So I total is going to be battery over just R1, and that will be the total current through the circuit, keeping in mind that the current through R2 is going to drop to 0 at that point. Okay, sketch a graph of the current through the battery as a function of time. All right, so through the battery tells us that we're looking at the total current. So what we're going to do is we're going to connect our answer to A with our answer to C with a 1 minus exponential decay curve. So our answer to C is going to be a bigger number since we're dividing by a smaller number. So E over R1. And it's going to start somewhere down here. They don't really tell us how far down. They don't give us relative values. And it doesn't matter. It's somewhere down here, but it's not 0. E over R1 plus R2. And we're going to have an upside down exponential decay curve that will approach the asymptote but never cross it. And if I had a pencil and paper, I would be trying to get closer to the asymptote. But what you don't want to do is cross the asymptote. Okay, now in part C, of course, they're going to change the rules on us. They're going to reopen the switch. So after it has reached steady state, which means the current in the circuit is I total E over R1. That's the current that we're going to play with. The current from part A is done. What's the voltage across resistor 2 just after the switch is opened? All right, once again, we come back to our basic idea in part B, which is right here. The voltage drop across R2 is the same as what's going on in the inductor. Now in part B, the events in R2 are driving what's going to happen in the inductor. When we get down to part E, now it's reversed. What's happening in the inductor is going to force something to happen in the resistor. So using a Kirchhoff loop rule, D minus, we're going to take a look at situation where we no longer have R1, we no longer have the battery, we just have these guys, and the inductor is sort of like acting like the battery for the resistor and forcing the current to continue going through the resistor. So the current is now going to go upwards through the resistor because it was going down in the inductor, and now our loop is just this right side here. So we're going to have V of the inductor minus V of the resistor, gets us to 0. And the current that we had going on in the inductor was this I total of E over R1, and the resistance for R2 is just R2. And see, what do they want? They just want the voltage there. So the voltage across the inductor is going to be this description here. So voltage across the inductor is going to be voltage across the resistor, which is E over R1 times R2. They are still the same. They've just been changed a little bit by the fact that the current has been built up, and the current is what we found in part C.